So what is the challenge with abrasive water jet technology? Well, one challenge is that it's a dynamic tool. It's not a geometrically defined tool. So this means that we have a jet with a certain energy and we have a material with erosion resistance. And the result of the combination of this jet and the material will be a tool that will be changing depending on the jet process parameters and the material parameters. Depending on the cutting speed, we will have the jet being deflected slightly by the materials. The faster we go, we will have more of a jet lag with the bottom of the cut lagging behind the top of the cut. Also in the taper and the width of the cut is depending on the cutting speed. So if we go fast, we will have a taper where the width of the cut at the top is wider than the cut at the bottom. If we go down in cutting speed, we will reduce the taper, and at some instance we will have parallel walls of both sides of the cut. And we will even get negative taper, meaning that we will have a wider cut at the bottom. The slower we go, we will also improve the cutting finish of the surface, so we will have a slightly lower surface roughness when we go slow. So, say to get a really good part in microabrasive water jet cutting, we want to go to a speed where we have no taper. If we have a 3-axis machine, we have to reduce the speed significantly to reach this part. It's almost 10% of the speed that we need to cut through the material. So what if we could go this fast? We know how much taper we have here. If we can have a database saying how much taper we have at a specific speed, we could compensate for this taper, and we would have a slight difference in roughness, but the roughness is fairly low change compared to what we gain in the taper control. To be able to collect data, to make a database, we have developed a methodology. So we have this test part here. It has room for 4 different tests. When we analyze this, we can get the data from looking at the top and the bottom. We can look at the width of the cut by measuring the width, and we can also see the lag by measuring how far the jet curve goes into the part at the top and at the bottom. So by doing these tests for a number of speeds and thicknesses, we will build a database to compensate for the certain material that we can build into the CAD/CAM system. The benefit of taper angle compensation would be that if we are able now to tilt the nozzle, then we can get all of the taper on the scrap side, and we get one part that would have a straight edge. And just to show the benefit of this, we have a data table of stainless steel. This shows the different cutting qualities and the speed at different material thicknesses. And typical for the water jet business is that we use quality levels for describing different quality of the cut surface. And the quality level number 9, that means that we are cutting without any taper. And the quality number 1, that means just a separating cut. So if we want to cut, say, 5mm stainless steel at a very high quality cut with no taper, we will need to go down to 18 millimeters per minute in cutting speed. But if we look at the surfaces we produce, we can see that if we go down to quality number 5 or 4, we will still have no striation. We will have a quite good surface quality. And if we move to quality number 4 and have an adequate surface quality there, we can almost double the speed for this material. So this is very interesting benefit of using the 5-axis control. When we build 5-axis control, we can do that in different manners. One way to do it is to tilt the jet with one axis and to tilt the part with another axis. Another way is to bring two axes on the jet and to tilt it in two directions. For this test we have been using the manipulation system that tilts the jet in both axes, and to prove the efficiency of this setup we have made a case where we have a medical device part in titanium. This part has a tolerance requirement of plus minus 10 microns. It's made from 3 mm thick titanium. The taper of the cut must be within tolerance as well, and we need to have an RA value below or equal to 1.6 micron. And of course we would like to have a productive cutting speed for this part. When we were trying this, we have been making test cuts. We tried to cut with the 3-axis setup, and to get straight walls with no taper we had to reduce the speed to approximately 30 millimeters per minute. And it was still difficult to get rid of all of the taper for this part. If we use the same machine setup and increase the speed to quality 5 and quality 4, we could obtain approximately 80 millimeters per minute in cutting speed, but that would mean that we would have about 80 microns in taper between top and bottom, which is not acceptable, but we will still have an acceptable surface finish. So what we do now is that we want to compensate the taper by using the 5-axis control, and we went to cut with quality number 4 with the speed of approximately 80 millimeters per minute, and we were actually able to reduce the taper to 0 and still maintain the 1.6 micron in RA value. So this shows that it's possible to use 5-axis control to reduce the taper and still produce high precision parts. Of course, when we make a machine with a 5-axis control and 5-axis mechanics, that would add cost to the machine. We will have a base investment that have a payoff time, and this will put extra cost on the part that we cut. So if we cut the part, we will also have a running cost for the part, and the running cost will add up to an accumulated cost for a series of number of parts over time. But if we use the 5-axis machine, that would add to the investment cost, that would be higher. So the 5-axis machine would cost more, but we cut quicker, so we will have less running cost for each part, so we actually reduce the running cost by 60%. And this means that when we are cutting a number of parts, the running cost will, the accumulated running cost will increase more slowly, and for this specific part we will have a payoff time that is approximately of 1 year. To sum this up, we can see that the 5-axis manipulation has the potential to bring substantial benefits for productivity and economy in microabrasive water-jet cutting. In this current case, it has shown that taper can be eliminated and part can be cut within tolerance. We see that we get typically 15% higher surface roughness. Here it's approximately difference of 0.2 microns. And we have the potential for increase in productivity of 134%. We cut more than twice the cutting speed, which gives us the opportunity to get a payoff time in the range of 1 year, typically. So with this, I thank you very much for your attention.